Welcome to Frontiers of Research. I'm Antoni, and today we're taking a fascinating journey back to the late 1970s, exploring one of the most remarkable developments in mathematical logic. We're joined by Dr. Rachel, our mathematical logic expert, and Josh, who'll help us unpack these complex ideas with insightful questions. Today's episode is particularly special as we delve into a revolutionary period in mathematical logic that changed our understanding of what can and cannot be proved in mathematics. The work we'll discuss today stands alongside Gödel's famous incompleteness theorems in its profound implications for mathematical foundations. We'll be discussing the groundbreaking work of Jeff Paris and Lawrence Kirby, who discovered natural independence results in Peano Arithmetic. Their work showed that certain seemingly simple mathematical statements cannot be proved within the standard framework of arithmetic. This discovery was revolutionary because, unlike previous independence results that were specifically constructed to be unprovable, these were statements that mathematicians might naturally encounter in their research. Before we dive into their specific discoveries, it's worth noting that Paris and Kirby's work came at a time when mathematical logic was already a well-established field, building on the foundations laid by giants like Gödel, Turing, and Cohen. Yet they managed to find something entirely new and unexpected.
Before we dive in, could you explain what we mean by independence results and why they're significant in mathematical logic? I imagine many of our listeners might be familiar with the concept of mathematical proofs, but the idea that some statements can't be proved or disproved might seem counterintuitive.
Certainly, an independence result shows that a mathematical statement can neither be proved nor disproved within a given formal system. The most famous example is Gödel's incompleteness theorem. What made Paris and Kirby's work so remarkable was that they found independence results that were natural and combinatorial in nature, rather than being constructed specifically to be independent. Let me give you a concrete example. Imagine you're playing a game with finite mathematical objects, following clear, simple rules. You might naturally wonder whether this game always ends. Paris and Kirby showed that for certain games, even though we can see that they must end, proving this fact requires mathematical principles beyond what's available in Peano Arithmetic. This is fundamentally different from earlier independence results, which often involved statements that were deliberately constructed to be self-referential or logically complex. Their work showed that independence phenomena arise naturally in mathematics, even in seemingly straightforward situations involving finite combinatorics.
Let's start with Jeff Paris's work. His 1977 paper demonstrated something quite remarkable about certain sequences of numbers. This work, which later became known as the Paris-Harrington theorem, was a watershed moment in mathematical logic. It showed that independence results could arise from natural mathematical investigations, rather than being artificially constructed.
Yes, Paris showed that the statement about the existence of certain sequences, now known as the Paris-Harrington principle, is true but unprovable in Peano Arithmetic. This was the first natural combinatorial statement known to be independent of PA. The principle is a strengthened version of Ramsey's theorem, and what's fascinating is that it's perfectly meaningful and true in ordinary mathematics, yet its truth cannot be established within the formal system of Peano Arithmetic. Let me explain the principle in more detail. Imagine you have a large group of people, and you're looking at all possible subgroups of a certain size. The Paris-Harrington principle states that if you color these subgroups with a finite number of colors, you can always find a large, homogeneous collection where the size of the collection is at least as large as its smallest element. This is a natural extension of Ramsey's theorem, but it turns out to be just strong enough to escape the bounds of what can be proved in Peano Arithmetic. The proof of this independence involves sophisticated techniques from proof theory and model theory, showing how seemingly simple combinatorial principles can have profound logical significance.
Could you break down what makes this result so different from earlier independence results? And perhaps give us a sense of how mathematicians reacted to this discovery. It seems like this would have been quite shocking to the mathematical community at the time.
Earlier independence results, like Gödel's sentence, were essentially constructed to be independent. They were statements about the formal system itself, but the Paris-Harrington principle is a statement about finite combinatorics, about actual mathematical objects and their properties. It's the kind of statement a mathematician might naturally encounter while studying combinatorics, without thinking about logic or formal systems at all. The reaction in the mathematical community was, indeed, one of surprise and excitement. Here was a statement that could be explained to any mathematician without requiring deep knowledge of logic or formal systems, yet it exhibited this remarkable independence phenomenon. This opened up a whole new perspective on the relationship between ordinary mathematics and formal systems. It suggested that the limitations of formal systems like Peano Arithmetic weren't just curiosities of mathematical logic, but could have real implications for everyday mathematical practice. Some mathematicians began to wonder what other natural mathematical statements might be independent of various formal systems.
This brings us to Lawrence Kirby's fascinating work on the Hydra game. Rachel, can you tell us about this remarkable mathematical creature? This is perhaps one of the most visually appealing and intuitive examples of independence in mathematics.
The Hydra game, developed by Kirby and Paris, is a beautiful mathematical metaphor. Imagine a tree-like structure where cutting off a head causes new heads to grow according to specific rules. Kirby showed that while you can always win this game by following a simple strategy, proving that this strategy always works cannot be done in Peano Arithmetic. It's a wonderfully concrete example of an independence result. The beauty of the Hydra game lies in its simplicity. You can explain it to anyone who understands trees as mathematical structures, and you can even play it with paper and pencil. Yet, this simple game encapsulates deep mathematical principles about growth, recursion, and the limits of formal systems. The fact that such a concrete, visualizable mathematical object could lead to independence results was a major breakthrough in making these abstract logical concepts more accessible and tangible.
That's fascinating. Could you elaborate on how this game actually works? I'm particularly curious about the specific rules and why they lead to this surprising result. Also, could you explain what it means practically that we can't prove the winning strategy works in Peano Arithmetic?
In the Hydra game, each time you cut off a head, the Hydra grows new heads based on the height where you made the cut. The remarkable thing is that a simple strategy, always cutting the leftmost head, will eventually defeat any Hydra. However, proving this requires mathematical principles that go beyond Peano Arithmetic. This connects to fundamental questions about mathematical induction and what we can and cannot prove within formal systems. Let me walk you through a specific example. Imagine a Hydra with just 3 levels. When you cut a head at the lowest level, nothing special happens. But when you cut a head at a higher level, the Hydra responds by creating multiple copies of the structure below the cut. What makes this game so fascinating is that even though the Hydra can grow enormously complex very quickly, with potentially millions of heads after just a few moves, we can prove that it must eventually be defeated. The proof requires a form of transfinite induction up to E0, which goes beyond what's available in Peano Arithmetic. This means that while we can understand why the strategy works, formalizing this understanding requires stronger mathematical principles than those available in basic arithmetic.
These results really changed how we think about mathematical independence. What was the immediate impact on the field? How did this influence the direction of research in mathematical logic and related areas in the following decades?
The impact was profound. Paris and Kirby's work opened up an entirely new approach to independence results. They showed that independence isn't just a logical curiosity, but appears naturally in mathematics. This led to a whole program of research looking for other natural independence phenomena, influencing fields from proof theory to computer science. Their work also sparked interest in what we now call reverse mathematics, the study of which mathematical principles are necessary and sufficient to prove various theorems. This has become a major area of research in mathematical logic, helping us understand the precise relationship between mathematical theorems and the axioms needed to prove them. The impact wasn't limited to logic either. Their work influenced computer science through connections with program termination problems and complexity theory. It showed that questions about what computers can effectively calculate are deeply connected to questions about what we can prove in formal systems.
How do these results influence current research in mathematical logic? Are mathematicians still finding new independence results? And how has our understanding of these phenomena evolved since Paris and Kirby's initial discoveries?
These results continue to inspire new research directions. They've influenced our understanding of proof complexity, helped develop new techniques in reverse mathematics, and even contributed to theoretical computer science through connections with termination problems. The search for natural independence phenomena remains an active area of research today. Modern researchers are exploring independence phenomena in various mathematical contexts, from set theory to category theory. We're also seeing applications in computer science, particularly in program verification and complexity theory. The work of Paris and Kirby showed us that independence phenomena are not just edge cases in the foundations of mathematics, but are deeply woven into the fabric of mathematical reasoning itself. This perspective continues to yield new insights and connections across different areas of mathematics and computer science. Recent work has even suggested connections to machine learning and artificial intelligence, particularly in understanding the limitations of formal reasoning systems.
Thank you, Rachel and Josh, for helping us explore these fascinating developments in mathematical logic. The work of Paris and Kirby stands as a testament to how seemingly simple questions can lead to profound insights about the nature of mathematical truth and proof. For our listeners interested in learning more, full references to Paris and Kirby's seminal papers can be found in our show notes. Their work reminds us that mathematics is not just about finding answers, but about understanding the fundamental nature of mathematical truth itself. Join us next time for more exciting journeys through mathematical discovery, where we'll continue to explore the frontiers of human knowledge and understanding.